Hi everyone. Previously, on our discussions on Schmidt triggers, we discussed how to realize Schmidt triggers with symmetric and asymmetric threshold voltages. We looked at how to analyze these circuits in great detail. In this lecture, I'll talk about the Schmidt triggers from a designer's point of view, from a circuit designer's point of view, and also very briefly summarize all the points that we have discussed so far, and also some other interesting ways of realizing Schmidt triggers with asymmetric threshold voltages. So I'll start with the discussion. Shown here are the voltage transfer characteristics of a non-inverting and an inverting Schmidt trigger here. Now if you look at this transfer characteristics, there are only two important parameters for a Schmidt trigger. One is the low to high threshold voltage, the other one is the high to low threshold voltage. Okay, what should be the low to high and high to low threshold voltages? That will decide what kind of a Schmidt trigger it is. And we already discussed this low to high and high to low threshold voltages determine the duty cycle at the output of your Schmidt trigger. Right? Schmidt triggers are popularly used as triangular wave or sinusoidal wave to square wave converters. And the duty cycle, and later we will see even the delay between the input zero crossing and the output zero crossing are determined by these threshold voltages. So that's why I thought I'll spend one lecture. How does an engineer go about designing a Schmidt trigger? Okay, so first I'll start with a simpler case of symmetric threshold voltages. Now, before I start the discussion, in this lecture I'm mainly going to stick with Schmidt triggers that operate on a dual supplies. Okay, if they operate on dual supplies, then the output can go to plus VSAT and minus VSAT. Okay, so that being said, I'll start with the discussion. So first, the simpler case of Schmidt triggers with symmetric threshold voltages. For a Schmidt trigger with symmetric threshold voltages, the low to high voltage, whether it's non-inverting or inverting Schmidt trigger, is simply equal to the negative of the high to low threshold voltage. Which means if I set my value of VLH, automatically the value of the high to low threshold voltage is set. So there is only one design parameter as such, right? If you talk about it, there is only one unique design parameter in the circuit. If you set that guy, the other design parameter automatically gets set. So shown here are the two popular circuits for a non-inverting and an inverting Schmidt trigger. So this one is an inverting Schmidt trigger. This one here is a non-inverting Schmidt trigger. And in both these cases, the low to high and high to low threshold voltages depend upon the factor beta. I'll first talk the simpler case. I'll first talk about the non-inverting Schmidt trigger. In the non-inverting Schmidt trigger, the low to high threshold voltage is given by plus beta VSAT, and high to low is given by minus beta VSAT, right? Just the negative of it. So as a designer, generally VSAT is fixed. That is determined by, it's usually closer to your supply voltage. So if you are to design the Schmidt trigger for a given given threshold voltage, then the value of beta gets fixed. What is beta? Beta is simply the ratio of the resistor R1 and R2. So if you see in this Schmidt trigger architecture, the ratio of the resistance is fixed, but not the absolute value of the resistors. Now, usually the absolute value of the resistors will have an impact on the performance as well. Once we start, maybe at some point when I have time, I'll talk about noise and the impact of noise on the Schmidt trigger's performance, noise of the resistors and on the Schmidt trigger's performance. But right now you can see that if you are to build a Schmidt trigger, what is important is not the absolute value of the resistors, but just the ratio of the two resistors. Okay, I can have the same low to high threshold voltage for different value of the resistors as long as their ratios are constant. Okay, the absolute value of the resistors usually get fixed by the power consumption of the op amp, how much power you can apply. And in some cases, I have seen this in some cases in the labs when we would ask them to build experiments. Sometimes students end up using op amp ICs to build comparators, Schmidt triggers. And when they do that, we see some very interesting stability problems. Okay, And so I'll talk about those experiments at a much later stage. But right now, what I'm trying to convey here is that to design a Schmidt trigger with a given threshold voltage, it's only the ratio of the resistors that matter, not the absolute value of the resistors themselves. In the next lecture, I'll talk about Schmidt triggers with open collector and open drain outputs. There you will see the absolute value of the resistors will also matter. Okay, but generally the absolute value of the resistors, usually as long as you choose the resistors so that they are within the current driving capabilities of the op amp, you shouldn't really worry about it. Of the comparator IC, you shouldn't really worry about it. So in the same way, in case of an inverting Schmidt trigger, the low to high threshold voltage will be given by minus of beta Vsat, and again beta in this case is given by it's the feedback factor given by R1 by R1 plus R2, which can be written as 1 by 1 plus R2 by R1. Again, if you see, beta is dependent only on the ratio of the two resistor values, not the absolute value of the resistors. Okay, so if I have to design for a certain threshold voltage, then I have to choose the right ratio of the two resistors. That's it. From a design point of view, it's that simple. You just have to pick the two resistors meeting a certain ratio. Now coming to asymmetric threshold voltages. In case of asymmetric threshold voltages, the low to high voltage will not be, you cannot write a linear relationship between the two because they are independently set. Okay, in Schmidt triggers with asymmetric threshold voltages, your mod of low to high threshold voltage will not be equal to mod of high to low threshold voltage, right? In symmetric threshold voltages, this condition will be satisfied. Mod of low to high will be equal to mod of high to low voltage, but here this condition will not be satisfied. So there are two independent design parameters for the Schmidt trigger. Therefore, naturally, you will need two design variables. So previously there was only one design parameter, which is the low to high or high to low threshold voltage. Therefore, you just needed one design variable, which is beta, to set, which once you set the factor beta, automatically the threshold voltages are also set. But in case of asymmetric threshold voltages, there are two independent design parameters that a designer has to meet, that a designer has to take into consideration. Okay, so for that we have discussed the circuit realizations of Schmidt triggers with asymmetric threshold voltages. The first approach is to have asymmetric feedback. When the output is logic high, you have one kind of a feedback factor, and when the output is logic low, you have a different feedback factor. Okay, so that's what we discussed in the last lecture. I've done the analysis greatly, so I'll not go much into detail. So shown here is the transfer characteristics of a non-inverting Schmidt trigger with asymmetric threshold voltage, okay, all you have to do is just use diodes to make sure that the feedback factor is different for the different threshold voltages. Okay, the feedback factor is different for the different output voltages. If your output voltage is logic high, the feedback factor will be beta 2. If your output voltage is logic low, the feedback factor will be beta 1. Okay, where beta 1 and beta 2 are given by the variables here. I think this is not right here. Yeah, I'm sorry. So this is a non-inverting Schmidt trigger. So the value of beta 1 here is given here. Beta 1 is low to high threshold voltage, which means your output should have been low to begin with. So this should have been minus Vsat, which means it will turn on this diode. Okay, so the feedback factor beta 1 in that case is given by R by Rx, and the feedback factor beta 2 is given by, which will be your threshold voltage for the high to low transition, is given. High to low transition means your output is already high to begin with, then this diode will be turned on, so Ry resistance will be in the picture. So beta in that case is given by R by Ry. Okay, and the threshold voltages are given by low to high threshold voltages plus beta 1 Vsat, the high to low threshold voltages minus beta 2 times Vsat. So now here if you see, we have two independent feedback factors, right? For two different threshold voltages, the feedback factors are different. Therefore now you have two design variables to tweak, beta 1 and beta 2. So again, the ratio of the resistors You just have to set the ratio of the resistors. The absolute resistance values don't matter here. As long as they are within the current rating of the diode and the comparator, you should be fine. In case of comparators with open collector or open drain outputs, we will have to take into consideration about the logic high and logic low levels and all that. So I'll talk about that when I talk about open collector and open drain outputs. Okay, so right now all I'm trying to tell you here is that there are two design variables, which means you will have two design equations, and there are two unknowns in these equations. The two unknowns are beta 1 and beta 2. You just have to solve for them and find beta 1 and beta 2. Once you know beta 1 and beta 2, the ratio of the resistors gets fixed. Okay, so once the ratio of the resistors gets fixed, so it's a very you can choose the value of the resistors to be different, but as long as they meet the ratio, you will have the desired threshold voltages. Similarly, in case of a non-inverting an inverting Schmidt trigger, the factors beta 1 and beta 2 are given by R by R1, but here R is in the feedback path, R is in the connected to the non-inverting terminal. So the factors beta 1 and beta 2 are known. So all I'm trying to say is that there will be two independent variables that you have, and two independent equations and two unknowns in these two equations. You can just find out beta 1 and beta 2, and beta 1 and beta 2 will decide the ratio of the two resistors. The absolute value of the resistors is not determined. It's not something you can uniquely determine from these equations. Okay, those things usually come from noise, and in case of open collector outputs, the logic low level, how low can the output go, that is determined. The ratio of the resistor, absolute value of the resistors, will be determined by that. The other case of Schmidt triggers with asymmetric threshold voltages is by adding offsets. We discussed two cases for non-inverting and inverting Schmidt triggers, how the circuit changes when we add offsets. We took a simple example of adding offsets. In case of non-inverting Schmidt trigger, you can just feed some reference voltage through a potential divider to the inverting terminal instead of connecting it to ground. Then we said that amounts to shifting this graph by Vref volts to the right. Okay, if you apply a negative voltage, Vref is negative, then you will shift it to the left. Okay, so now here the low to high and high to low threshold voltages are given by beta Vsat plus Vref minus beta Vsat plus Vref. Remember, the feedback factor is the same both for high to low and low to high threshold voltages. The feedback factor remains the same. The only difference is we have added a fixed offset voltage, fixed reference, or in this it's an offset voltage. Here the offset voltage is equal to Vref. So now again there are two unknowns. Low to high and high to low threshold voltages are independent. So there are two unknowns and you have two equations to solve. Okay, these are two linear equations to solve. You will get two values you will get unique values of beta and Vref. Okay, Vref is a voltage, so there is a unique value for that. In case of beta, the ratio of the resistors gets fixed. So in this beta here in this circuit will be R1 by R2, and you can choose any value of R1 and R2 as long as they are within the op-amp's, the comparator's current limits. Okay, op-amp will have minimum and maximum currents that it can provide for, and as long as they are within those current limits, you can choose any value of the resistance. Okay, here we are not taking the noise into consideration, because remember, when you take noise into consideration, noise will also impact the threshold voltages. Okay, you will have some additional noise here that will determine the threshold voltage value. That will usually result in some kind of jitter at the output of the Schmidt trigger. So right now, if you're an undergraduate who's just learning these things for the first time, you don't have to worry about that. Okay, so as a designer, if let's say you're just an undergrad who is building these circuits in the lab, the only thing you will have to worry about is setting the ratio right. If you set the ratio right, then you can build a Schmidt trigger with asymmetric threshold voltages. You have to get the ratio right and the right reference voltage. If you set these two right, then you can then you have an Schmidt trigger with the asymmetric threshold voltages for the desired values, VLH and VHL. Similarly, for an inverting Schmidt trigger, the equations are a little bit more complex in this case. We have analyzed that in the previous lecture. So I'll just directly write these two equations. The low to high and high to low threshold voltages are given. So here if you see, again you have two equations and two unknowns here, but these two equations are non-linear. Okay, the unknowns are it's a non-linear equation, so you'll have to solve it graphically, or you have to solve it using a computer and figure out the values of beta and Vref. Again, beta will only decide the ratio of the resistors. Absolute value of the resistors don't matter for any practical circuit that you are building. The absolute value of the resistors will matter in when you are using comparators with open collector or open drain outputs. Okay, keep this point in mind. I'll later talk about this and you will understand why it matters.